code, it always seems like we come back to the concept of arc length. You know, it's like we get away from arc length and then we come storming back to it because it's that important. Right? So what we're going to learn about is actually how to start defining functions in terms of its arc length. Right? So, you know, the objective is pretty obvious. You have your arc length formula for a vector valued function. Now, that's actually, if you look at it, it's very similar to the arc length formula for parametrics in 2 dimensions, except we're adding a 3rd dimension, right? But if you really think about the structure of it, it has an awful lot of similarity to the formula for distance or magnitude. And so that's actually what's happening here, because if I were to take the magnitude of the derivative of a vector value function, that would actually become my integrand, right? So, for example, well, maybe not example, just to kind of justify it here. If I wanted to find the magnitude of R, not R prime, just R. You know, just think it back to the last unit. What I would do is take my components, my vector valued function, which would have the components f of t, g of t, and h of t. I would square each of those. And then take the square root. So that's our magnitude for a vector valued function. You know, we didn't really do much with that in the last unit. We found derivatives and antiderivatives and stuff, but we could also, it behaves like a vector, so why wouldn't the rules for vector relationships come into play, like magnitude? You know, so you could also come up with a unit vector in the direction of R of t, which would actually be just disgusting, right? So, because what you would be doing is dividing your vector value function by the magnitude, or really just distributing through 1 over the magnitude of the vector value function, right? So the unit vector in the direction of R of t would be 1 over the magnitude multiplied by R of t. But, and we'll get to that, we'll get to the meaning of that kind of thing in a little bit, but for now, we're just kind of expanding that to the idea of, okay, well, what if you have R prime of t? So R prime of t, that's clearly not an R. R prime of t would be equal to, I'll write it in vector form, f prime of t, comma g prime of t, comma h prime of t. So the magnitude would follow the same form, except have a bunch of primes in it. All right, so what we're actually kind of doing is going the other way. When we look at arc length, we knew that in 2 dimensions that it was Pythagorean in nature. It was, you find the horizontal component, you square it, you find the vertical component, you square it, and then add them together and take the square root. When you get into the 3rd dimension, you throw into the mix a 3rd dimension. But as it turns out, and I meant to put a prime here, as it turns out, that happens to also be the magnitude of R prime of t. Right? So notation-wise, it tends to be a lot simpler, but it's still an operation that needs to be carried out. Right? So now in terms of creating a graph and coming up with the arc length, you know, it's easier said than done, because depending on the nature of the relation, it could be just difficult to type into Geogebra. Right? So I wrote the little notation here. It's often impossible to find the antiderivative of the integrand exactly, so we'll usually have to settle for an approximate numerical answer to our arc length calculations. All right, so that's a possibility. And you'll see some circumstances where that comes up. But when we can figure it out, it's really gratifying. Right. So in number 1, it says compute the arc length for the curve traced out by the vector value function, cosine sine t. So I'll write that in component form. So I would differentiate each of those components, come up with r prime of t. And then find the magnitude of that r prime of t. And we get that by squaring each part, adding them together, and then taking the square root. So that becomes sine squared of t, the negative squares away, cosine squared t plus 1 under a radical. Now, it's kind of nice when you recognize this. Well, that is a very thin highlighter. I need something a little thicker. When you recognize those trigonometric identities, it's really nice because that streamlines the amount of work that you have to do. Right? That's the same as saying 1. So we're looking at the square root for quality square root, as in that's not a square root symbol. I'm just going to hand draw it. So we end up with the square root of 1 plus 1, which is the square root of 2. All right, so it turns out that the magnitude of the derivative of the vector valued function is equal to the square root of 2. Now, that's not the arc length, but that's a step in the direction for figuring out the arc length. So we now know that S, which stands for arc length, is going to integrate over the interval of 0 to 2 pi the square root of 2 with respect to t, which is going to give us the square root of 2. Let me move that over because I forgot to put the t in. The square root of 2 times t over the interval of 0 to 2 pi. So we're looking at 2 pi radical 2. So that would be my arc length. And it's all based off of your ability to find a derivative and the magnitude of that derivative. Right? But what I want to, yeah.
After the line of r prime of t, did you change the negative sign of t to just sine squared of t because you squared it, or?
Yeah, exactly.
Okay.
Yeah, no problem. All right, so what I'm going to do is I'm going to pop it into Geogebra. I'm going to do more of a half and half split screen just so I have a better view on Geogebra. Yeah, so we use the curve function when we put in a vector valued function. Curve. Now, this happens to me all the time. It's really annoying. What I've done, and I don't know if you have to deal with the. I'll get to the chat in a second, but I don't know if you have to deal with the touchscreen issues that I have to deal with, like if you're trying to do it on your phone. But what I do when I'm typing in curve is I just kind of tap something other than anywhere, when that drop down comes down, it messes everything up. So I want, curve, then it gives the suggestions, and I know it's all over if I tap one of these things. So what I do is I just hit that little Greek letter tab just to kind of get rid of that. Then I go back into the regular QWERTY pad, finish typing curve. Oh, that's not an E. It's a real royal pain, but you eventually get there. But it's a kind of problem that you only really have with a touchscreen. All right. Now, if you're using an iPad and you're dedicating the full screen to this, it shouldn't be a problem. But if you're trying to do it on a phone, I can see how that could be tough. But eventually, you get the word curve in there, and then you're just going to type in the relevant components, so cosine. So I just kind of keep going back and forth with that that Greek alphabet, just to kind of get me out of that drop-down display. So cosine t, sine, it does the drop-down thing. It's in my way. So I tap on the Greek alphabet, puts me in the Greek alphabet, but it makes the thing go away. Then I go back in, open parentheses, T. I mean, it might be that the lesson that we're learning here is don't use a touch screen to do this, but I kind of have to, the way the Zoom setup is. So I have my 3 components in, cosine t, sine t, t. Now I have to define my variable as t and then give it a domain. Now, in this case, we're only going from 0 to 2 pi, so you can put that in. You could put it in as decimal values. It's up to you. 0 to 2. You just type in a pi. Do I have a pi? Yeah, I have a pi right there. 0 to 2 pi. Then lock it in, and you can see here that what we're looking at is a spiral of some kind. All right. Now you saw it in the diagram on the page, but that's a 2-dimensional rendering of a 3-dimensional figure. So that's always going to be tricky. But here we can do you can get a little bit of a better view. And if you give it the top-down look and give it kind of a spin, you see that it does have a circular aspect to it. All right. So just so people don't get disoriented, I'll stop manipulating it. But it is a spiral, and what we're looking for is the arc length of that spiral. So what we just got is that the length of that curve is 2 pi radical 2. All right. And honestly, it's kind of crazy that all this time I haven't tried this yet. I'm going to give it a shot. You see now it's completely in my way. So you know what I'll do? I'll just type in the wrong letter. No. Okay, so G T H, and then let's see if it'll figure out the length of A. I wouldn't think it would, but you never know. Figured I'd give it a shot. Yeah. Curve, start, endpoint. Okay, I'll try it with the start and endpoint. 0, 2 pi. 8.89. All right, so the moment of truth, 2 pi times the square root of 2. 8.89. What do you know? Honestly, first time I tried that. Never tried it before, so good to know that it'll actually figure it out. That's cool. All right, so that's a means by which you can come up with the answer without even doing any calculus. Right, but my mouse not working. It's like a disaster waiting to happen here. Okay, so that's for attendance. I'll get that. All right, Michael, I'll get you for attendance. All right, so yeah, now you have the means by which you can come up with this, but you can already see, like, especially with a touchscreen, it's a pain to type it in. So I'm not going to say that you need to do pages of calculus just because it's hard to type something into a calculator, but part of you has to be like, well, if it's a simpler situation, maybe I'll do it by hand this one time, maybe I'll do it on the calculator that time. It's really up to you, but just be strategic is really what I'm getting at here. Sometimes it takes me a while to get what I'm trying to say out, unfortunately, but that's really what I'm getting at. Like, if it's a multiple choice question and you don't have to show me any work, then by all means do it on the calculator, do it on Geogebra. That's fine. That you're not going to run into a problem with me on that. I always have this rule of thumb when it comes to grading multiple choice questions. If you get a multiple choice question right, I don't go looking into your supporting work to find ways to take off credit. It's only if you get it wrong that I go into your supporting work looking for ways to give you credit. And so if this happens to be a multiple choice, more power to you. Put it into Geogebra, you'll get your answer, and there you go. But obviously, you want to be prepared to do it by hand. Right. So number 2 is along the same lines. If you're doing it in GeoGebra, it's really just a matter of changing your vector valued function. So you just got to tweak it a little bit. Popping in powers can be somewhat challenging. So I could put in a 5, and if it'll let me do it, I'll do it. I'll also do it by hand, just so you see, but I'm going to power 3 in there. Then 3 cosine. Oh, you see, I already got it backwards. All right, so this one is going to be sine. This one's cosine. So 3 cosine 3, or 3 cosine cubed is what I meant to say. We still got the t there. It's still going over the interval of 0 to 2 pi, so that's good. I'll lock this in if it'll let me. Whoa, that's funky. I mean, I kind of expected it because that's what the image looked like in the on the handout. I gotta say, honestly, the shock comes from the fact that I honestly expected that I would have screwed something up here. So the fact that it kind of worked out is kind of nice. Although it does seem to be somewhat backwards from the way I have it on there. So I'm just double checking. So I might have messed up one of them, either the handout or what I just typed in. It looks like I got what I typed in correctly. Well, regardless, this is what the figure looks like, and I don't think the static image on the handout page looks, or at least does it justice, because this looks definitely a lot more significant in terms of what's going on here. So this is a pretty crazy looking path, right? And so this is what we would need to figure out the arc length for. So we have it. It's 25.74. So I'll get rid of that other value. It's still over the interval of 0 to 5. It's just we got to make the calculations jive with that. Right? So let me rewrite RP 5 sine cubed t, 3 cosine cubed t. I'm writing it in component form. I'm going to bring it in. R prime of t. The little chain rule going on here. So 15 sine squared t cosine t. Then 9 cosine squared t times negative sine of t. So it's really negative 9 cosine squared t sine t. And a nice looking 1 at the end there. Right. And so that's what we got to figure out the magnitude for. And so we're going to square each part. And again, just like the last one, any negatives are going to zap away. So that's good news. Start relying on that kind of thing happening. All right. So 225, well, it's magnitude. So it's going to be a radical eventually. I'll leave the radical off for a second though. 225 sine to the 4th t cosine squared t minus, oh, well, really plus, right? So because we're squaring and adding, so plus 81 cosine to the 4th t sine squared t plus the 1 at the end, all under the radical. Yeah, I wish. Let me at least get the line in there. All right. So if we're going to make this work as part of an integral, we could do it one of two ways. We could type all this into, I would go with Desmos, because you've already seen just how tough it is to navigate GeoGebra, and not just from me, from doing the tech assignment, right? Yeah, so there's that part of it, but the other part would be, like maybe it won't be so bad to do it by hand if we clean it up. One way or the other, I think it's a good idea to clean it up a little bit because we're going to make it easier to either type it into Desmos or continue doing it by hand. All right. So I'm looking at this and I see a couple of common factors that can be pulled out, at least from the first part. You can't take it out of the whole thing, but maybe that's enough to get it going where it needs to go. And sometimes it's not, and if it's not, then you go to the calculator. It's a risk reward kind of thing. You got to look at it and say, is what I'm about to do worth the time I'm going to spend doing it? All right. If it is, then keep going. If it's not, then try something else. All right. So here, numerically, I'm not seeing a common factor because I guess you pull out a 9 in both cases, so that there's something there, but that you don't have the nice common factor where you could actually pull out the entire coefficients. But we'll see, because the factors of 225 are 15 and 15. So 3 times 5, 3 times 5, so 9 times 25. So we can make, I'm just going to write it down here so I don't have to zoom all over the place. But I could pull out a 9. That's not a marker. I could pull out a sine squared t and a cosine squared t. And when I pull that out, I'll be left with a 25 sine squared t. I'll resize this and move it around in a sec. Plus 9 cosine squared t plus 1 all under the radical. All right, so let me resize and move some things around here. And I'll bring it in again. All right, so again, it's the risk reward kind of thing, because I can now take well, actually no, I got that 1 there, so it's like all over at this point. I mean, if I wanted to, I could try to make that 1 into something else, like an old Calc 2 trick where you add something and subtract something to make it equal to a 1, or you can change the 1 into a sine squared plus cosine squared and see where that goes. I don't think any of that's going to get us anywhere. So, we tried it. It doesn't look like it's working out too nicely. So I think we're at that moment where it's like, listen, I think our best bet is to just pop this into the calculator and just let it work its magic. Other options, other possibilities, if you really want to go down the road, you have sine squared and cosine squared values. So you could actually, I'll actually show you the next step, just so in case you do want to go down that road. You could replace either the sine squared or the cosine squared with its Pythagorean identity equivalent. All right, so I'll replace the cosine squares. So we would actually make this 9 sine squared t times 1 minus sine squared t, 25 sine squared t plus 9 times another 1 minus sine squared t, and then plus the 1. All right. So if you distribute and clean things up, maybe things will end up being nicer, but it's already like I could have typed this problem in like 5 times already by the time we're at this point. All right. So, it's really it's not ending up being the beneficial use of your time. I don't think. Right. There could also be a transformation that you can make where you can use a trig substitution and clean things up. But again, these are things that are kind of beyond there. So that's what you would do. I don't really recommend that. What I would do, let me delete that, is now, as ugly as it is, get that into the calculator and call it a day. We just want to get out of here with a win. So I go to Desmos when I do this because, like I said, I mentioned this before. The GeoGebra interface is just so clunky that it's if I'm gonna screw something up in GeoGebra, honestly, if I'm gonna screw up the problem, I want it to be because I screwed up the problem, not because something happened in GeoGebra that caused the screw up. You know, I got to imagine there's at least a couple of people who agree with me. Maybe not. We'll see. It's up to you which version of this you want to put in. I'm just putting in the most recent one because I figured, you know, I typed it, so why not? I'll use X's. I'm not typed it. I wrote it. I should say. Cosine. You just got to backtrack to get the power of 2 in there. I'm only bringing that up because some people didn't know that. You can write, you know, like an old TI language. It would bring up like the sine of X, you know, sine open parentheses, you put the X in close parentheses, then you could square it. You could do that, but you could also backtrack. GeoGebra understands it in the proper notation too. Right? So it's really up to you how you want to write it. 25 sine squared X. Again, I'm using X in lieu of T, plus 9 cosine squared X in lieu of the T again, close it up, plus 1, close it up, pop on a dx, and you get your arc length, which is approximately 25.739. Okay. So, you know, that statement that I wrote up there, it's often impossible to find the antiderivative of the integrand exactly. You know, that I didn't know really how else to write it. I'll take it as a typo if somebody could think of a nicer way to explain that. But it's really more like sometimes, so this is what I really want to say. Sometimes it's too much of a pain in the ass to try to figure it out in an exact form that we use technology. So you just got to figure out how to translate pain in the ass into something that I could actually write in the handout. So if you can come up with a new phrasing on that, I'll take that as a typo. And actually that goes for like everything, you know, rephrasing of questions to make it sound, you know, like more intelligent, logical, you know, things like that. That's always a good thing. All right. Now, we're not just working with the computational stuff because honestly, this would be more like a Calc 2 kind of concept if it were computational. You know, aside from the fact that there's vectors involved, it's still the idea of finding definite integrals. What we want to do is start getting into more symbolic expressions, right? So, and that's where the fundamental theorem of calculus, part 2 of it, is going to come into play. We'll see that in a little bit. Anyway, the next example has got a little bit more beef to it. So let's find the arc length for the curve formed by the intersection of the cylinders, x squared plus y squared equals 9. And y squared plus z squared equals 1. Now, you can look at the intersection on GeoGebra of these two cylinders. You may not even recognize it necessarily as a cylinder at first. It takes a little experience, but it's actually one of the it's actually the third tech assignment that'll really kind of drive that stuff home. But basically these have the form of circle equations. It's just the variables aren't always just x and y, as you can see in the second equation. So what we assume, depending on the dimensions that you're working with, is that everything else, every other variable that's not represented in the equation is a free variable. So therefore, z is free. And in this case, x is free. And when we say it's a free variable, it's free to be whatever makes sense for it to be, whatever it's possible for it to be. And so what a lot of people assume is that that represents a domain of negative infinity to infinity, but we also allow for complex numbers and things like that, right? So that gives, for example, the x squared plus y squared equals 9 variable height in z. So a circle that could have a height, circle with height would be a cylinder, right? Now, y squared plus z squared is a circle that's living in the yz plane that has, I'll say, variable depth, right? It's a circle that's kind of looking at you, and it could come towards you or away from you, in which case that would indicate that the x variable is free. You could pop that into GeoGebra, but in a lot of cases, it's just nicer to be able to visualize it in your head, right? And I would even say, at some point, you want to kind of graduate to the level where you can just kind of visualize this stuff. Right? It takes a little doing. Kind of like when you first got your first graph in calculator, and you just started playing around with the different functions. Like you typed in sine. It was probably sin at that point. Like what is this? What does that look like? What does that log thing look like? Well, that doesn't look like a log, like a physical log. These are all certain. These are things that you can look at and say, these are the analogs to those moments. Way back when, right? So I just typed in x squared plus y squared equals 9. Maybe you had no idea what that would look like beforehand, but the more times you type it in, the more you start realizing that there's a consistency to these things. So y squared plus z squared is equal to a 1. And you can see we're looking at two intersecting cylinders, and the intersections of those cylinders form a circular path, right? So that circular path, now, when I say circular, I mean circular, not necessarily circle, right? So that's something to bear in mind. It may very well turn out to be a circle. I just want to see if I can change the color on one of them. I'm officially at the point where I'm getting my Desmos and GeoGebra confused with one another. But you could see here that there is like the little faintest shadow of an intersection between the red cylinder and the blue cylinder. If you look closely, you kind of see it there. You can kind of look down the shaft here and you can see, the red on the inside of that cylinder. That's where it meets the other cylinder. The outline of that, the circumference of the blue cylinder intersecting the red cylinder, that's what we're after. But you got to also understand it goes through on the other side as well. Right? So we want to find the sum of those intersections, because we said find the arc length of for the curve formed by the intersection of the cylinders. Right? It was non-specific. If it said just find the arc length, framed as like a word problem, a cylinder is approaching another cylinder as it intersects, as it first makes contact with the circumference or the surface of the other cylinder, what would be the arc length of that intersection? That's not really what's happening here. It's saying that there's an intersection, and we got to figure it out. We got to figure out what's going on here. Right. So the first thing that we need to do is determine, well, what the path is of that intersection or those intersections. So what I can do, because I see I have a system of equations in 3 variables, 2 equations, 3 variables. So one of them is going to be free when I solve this system. But what I can do is I can swap out. We have a common y squared. I can swap out one of the y squareds. So I'll take the x squared and solve that in terms of y squared. And then I'll replace the y squared not quite. Right. I'll replace the y squared with what with what I now know that it's equivalent to. Actually, I have to replace, I solve for x squared, so I got to replace kind of a schlemiel sometimes. Yeah, I probably should have solved for the y squared. Ay. That's not good. Anyway, so solve in the x squared plus y squared equals 9. Solve for y squared so I can make that substitution in terms of x. Good boy. Is it the end of the week yet? We're getting there. Right, so make that substitution, clean it up. You know, we want to be able to nail this down so that we can have a vector valued function that represents the intersection of the two surfaces. So as long as I get x equals this, y equals that, z equals that, I'll be in pretty good shape. All right. So we already know what y is equal to in terms of x. So let's solve for z in terms of x. So z squared would be equal to 1 minus 9 minus, well, minus a negative, so plus x squared. So negative 8 plus x squared, or you could write it as x squared minus 8. Right? So, hey, just moving things around, that's all. So then what that would tell us is that the z squared value would be the free variable. All right? So we have a relation here that says x squared, oh, I'm sorry, x squared is the free variable. X squared is free. Y squared is 9 minus 9 minus x squared, and z squared is negative 8 plus x squared, or x squared minus 8. All right, x squared minus 8. I think that makes more sense. All right. So these are some relationships that we have. We could also kind of clean it up a little bit more, but you know, we're kind of moving in the right direction here, right? Because the squared values, you know, obviously take the square root of both sides, and you'll have the appropriate relations. But the one thing we have to consider is that, well, that's going to introduce some pluses and minuses. So we got to be really careful about how we navigate from here on out, right? So that's what I'm going to do, is I'm going to write this as x squared is equal to, and we can actually make a decision of what we want x squared to be equivalent to. If I wanted to let x squared be equal to t, I would be creating a root within my expression, which might simplify things, might not. But I could also let x squared be equal to t squared, right? And you know, for the sake of making things simpler, that might be the way to go. All right, so y squared would be equal to 9 minus t squared, and z squared would be equal to t squared minus 8. All right, and so t is our parameter, and then it's just a matter of taking the square root. And so I'd be looking at x is equal to t, y is equal to plus or minus the square root. My square roots are just not in sync today. 9 minus t squared. And then z is going to be equal to the plus or minus square root of t squared minus 8. There. So all that is just to get me to a point where I have a vector valued function. You know, it's written as a system of equations, but its sole purpose is to get me to a point where I can actually start the process of finding the arc length. I'm just resizing and moving something. Oh, hello. Oh, this I can actually read. It's going to reset. I'm just grabbing the wrong thing consistently. close enough. I'll clean it up later if I need to. All right. So when I create in Geogebra the curve function, which is going to be even more of an adventure, I got to keep in mind that I have those pluses and minuses. All right. So I'm going to start typing that in just to make sure that I'm on the right track here. I want to make sure that I'm creating the appropriate relation. All right. Oh, I already screwed that up. Curve. All right, so now I can apparently talk too soon. Okay. Ooh, geez. So T, comma. I'll go with the positive roots to start. So the square root of 9 minus T squared, comma, then another square root, and this time it's T squared minus 8. All right. So then, comma, and what are we looking at here? Variable T. And then in terms of a domain, honestly, we can do whatever we want, but we can restrict it based off of what we see here. The T values are limited, right? So just kind of looking at this, I mean, it's up to you. You could try, just throwing in whatever you think, but we know that based off of this vector valued function, which I'll write as R of T is equal to the one I'm focusing on right now, T comma, the square root of 9 minus T squared, comma, the square root of T squared minus 8. The domain, well, based off of the T squared minus 8 and the 9 minus T squared, it's going to have a restriction. So 9 minus T squared has to be greater than or equal to 0. And T squared minus 8, same deal. Right, so T squared has to be greater than or equal to an 8, which means that T, the T value has to be beyond the values of 2 radical 2 or negative 2 radical 2. So more than 2 radical 2 or less than 2 radical 2. Right. Now in this case, I'm looking at negative T squared greater than or equal to negative 9. Divide out the negative, T squared would be less than or equal to 9. All right. So then what we're looking at is T having to be between negative 3 and 3. All right. So it kind of like gives us maybe a little less relevance to the radical 8 part of it. But, 2 radical 2, that's going to be something, north of the value of 2. So, you could say negative 3 to 3 and just see where that takes you, just so you don't spend too much time wrestling with domains. But we should also, at least have a sense. But really the whole purpose behind coming up with the curve part of this is to just at least make sure that we're coming up with the right intersection, like we have the correct vector value function, right? And you can see here, hopefully, kind of hard to tell, but you can see that we're getting about 1/4 of what we need, right? Because I got a little black curve on that one piece to the left and another black curve on that one piece to the right, but I also need the other side and the bottom half, right? So if I double this and double it again, so multiply by 4. So if I find the arc length of just this piece, then I'll have what I need. So all of this work here, the domain stuff, is really just to kind of, well, I'm going to need some bounds when I'm integrating. So there is a purpose behind that. but also just wanted to make sure I was on the right track. Right? So there's value in that regard also. But we can look at this and say that t has to be greater than or equal to, well, an 8, radical 8, I should say. I gotta figure out a way to do this so it actually doesn't look half bad. T rate is like 0.5, I think. Better. Radical 8, or t has to be less than or equal to negative radical 8. All right, and I'm not 100% sure without a calculator what radical 8 is, but I do know that it's less than 3, more than 2. Right, so I'm looking at something that's got to be greater than or equal to 2 radical 2, or less than or equal to negative 2 radical 2. All right, so in terms of a restriction to my domain, I would be thinking in terms of a number line. I'd be saying, okay, well, I have to be in between negative 3 to 3 for one piece, but beyond 2 radical 2 and negative 2 radical 2 for the other. Right, so just kind of sketch it out if you want, but or don't, that's up to you. But 2 radical 2 in decimal form is about 2.8. So here's 0, 1, 2, 3. I'm living only pause for dramatic effect in this interval to begin with because of this piece. But then because of this other piece, which is over here, I'm living beyond the 2.8 and the negative 2.8. So put it like here and about here roughly. So I can just kind of that. So we're looking at just this little interval here and just this little interval here. So it's a very small slice of domain that actually works for this whole thing, right? So I go back to my GeoGebra and tweak that domain. Instead of saying I'm going to go from negative 3 to 3, if the dang thing will let me. I'll try 2 radical 2 over to 3. All right. So I won't worry about the negatives for now and see where that takes me. So the t value is going from 2 radical 2 to 3. You see now that only gives me one piece of it. And you'd say, okay, well, it seems like we're going in the wrong direction here. Well, actually, not really. Because what that's telling me is now, okay, I have 1/8 of what I need. All right. So if I have 1/8 of what I need, then I can just take whatever integral I come up with for arc length and multiply it by 8, knowing that that integral is going to go from 2 radical 2 to 3. And then I'd be looking at r prime of t's magnitude dt. Right? So that would be the expression I'd be looking to set up, but now I have the bounds. All right. And so instead of figuring out each piece and adding them together, what I can do is this, multiply by 8, because now I have exactly 1/8 of what I need. All right. So what that means, well, aside from the fact that I did not give nearly enough space to do this problem, honestly, and it's really kind of strange because I do this problem every semester. I don't know why all of a sudden I need a ton more space. Maybe, honestly, I wonder if maybe I screwed it up in the past or something like that. I don't know. Anyway, we do need the derivative. And then on top of the derivative, we need the magnitude of that. Right. So the good thing about the magnitude part is at least the radicals are going to square away. The bad news is we got to take the derivative before that can happen. All right, so r prime of t, well, there's a 1. That's, yay, little win. This guy can be thought of as 9 minus t squared to the 1/2. So we're looking at 1/2 9 minus t to the negative 1/2 times a negative 2t. So we're going to have a 1, and then we're going to have, like I said, a 1/2, and then you'll have a negative 2t at the end. So 1/2 negative 2t is going to be negative t multiplied by 9 minus t squared to the negative 1/2. And the same idea would be kind of in play for the last piece. So again, could be thought of as t squared minus 8 to the 1/2. So that'd be 1/2 t squared minus 8 to the negative 1/2 multiplied by 2t. The 1/2 multiplied by the 2t will just give you a clean t. So then t squared minus 8 to the negative 1/2. And that would be the extent of it. You know, you could show more work, obviously, if that's something that you feel like you need to do, but you also don't have to. You know, there's a time and a place for that, and it's called Calc 1, right? So if I want to find the magnitude, I got to square each of those parts, then slap a radical over it. All right, well, easier said than done, but still doable. 8, 2 radical 2, 3. So 1 plus negative t is going to get squared. The 9 minus t squared to the negative 1/2. Well, when you square an exponent or exponential expression, you multiply the power by 2. So that's really just going to be 9 minus t squared to the negative first power plus t squared. Then we'd have, well, it's the same idea. So t squared minus 8 to the negative first power, all under the radical. Finally, I got my radical to work, dt. Now it's up to you at this point. You could try to clean it up manually, but recommendation would be pop it into Desmos. Really, it was just kind of like do as much work as it takes to get an expression that can be Desmos ready. So 8 multiplied by the antiderivative over the interval of 2 radical 2, going up to a 3, open paren, open a radical, 1 plus, I'll use x, so x squared times 9 minus x squared, close it up, raise it to the negative first power. That's assuming you don't want to make a fraction out of it. I didn't want to, so I didn't do that. Then another x squared, then x squared minus 8 raised to the negative first. So then inside the parens, zig when I should have zagged. Inside the radical, we're good. We don't need to close parens. Once we get out of the radical, we need to close parens. Then slap in a dx to indicate that we're anti-differentiating. And then parens, I think, it says I screwed up somewhere. Oh, I think I wanted to, okay, I see. I put my dx inside the parens when I should have put it outside. Should be an easy fix. There we go. So about 12.658 approximately, which I guess is what about meant. So 12.658. And dear Lord, what a problem. That one's crazy. It's a fun problem though. You know, so it just takes a lot of doing. And the thing that's easiest to lose track of would be the domain, obviously. You know, that stuff that I highlighted in green and purple. You know, you kind of get ahead of steam, and then you get to the part where you need to take an antiderivative and you say, oh crap, what are my bounds? And what some people do is they'll be like, well, it's circular, so it's usually like 0 to 2 pi, so let me just go with that. You know, doesn't always work. And sometimes you get lucky, but most of the time you won't. But definitely a fun problem. A lot of stuff going on there. But yeah, it takes a little getting used to. So we're going to learn how to parameterize in terms of arc length. All right. So I was about to flip the page, but then I realized, you know, one of my failings as a teacher over the years has been I write down a ton of stuff, and then right when I finish writing it, I'm like, all right, feel good about that. And then I flip the page and people are like, whoa, 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 you don't have a chance to write any of that down. What's going on here? So I figured I'd buy you another couple of seconds or two in order to be able to do that. But yeah, we're going to move on. We're going to talk about parameterizing in terms of arc length and also curvature. Really interesting topic, and also a really important one as we move forward. I can kind of talk a little bit about curvature while I'm killing time, because you know, the concept of curvature, you feel like you probably have explored that a lot. Like, oh, we've worked with curves a lot, you know, parabolas, ellipses, hyperbolas, things like that. But what about the curviness of a curve? Have you ever investigated that? Like, if I asked you, which one's curvier, a cubic function or a quadratic function? Some people might immediately say the cubic, because it has more, you know, peaks and valleys. Other people might say, well, the parabola, because that is a curve, you know, the whole thing is a curve. But then a person who's really kind of thinking about it critically might say, well, where on the curve are we talking? Are we talking at the vertex, where it's the curviest? Or are we talking like really far away from the vertex of a parabola where it's all, it might as well be a line at that point? You know, it depends on where you are. But there is a way that we can come up with a numerical value that represents the curviness of an expression or a function at a particular location. That's what we call curvature. Now, I mean, I think I could probably convince you that whatever the process is for coming up with the curvature value, it's going to yield a number. That number is going to be greater for a circle than it's going to be for a line. A line doesn't have any curvature at all. So the curvature value for a line would be 0. If the figure you're dealing with is not a line, then the curvature value would not be 0, it'd be something else. Right? But that's what we're working towards understanding. Right? But it's a really cool relationship, and it does have a lot of really useful applications. But before we get there, we have to talk about parameterization. Specifically, the idea of parameterizing in terms of arc length. Now, I talked about this way back in the beginning of the course, which isn't really that long ago, but it feels like a lifetime ago at this point. I drew a picture of a mountain, and or at least what you realized at the time was probably the best I could do in terms of drawing a picture of a mountain. But what's really happening, or what happened in there, and I'll give you the short version of it now. You have a mountain. So there's my mountain. And along that mountain is a path. And along that path is a person navigating, you know, making their way up the mountain. Okay, so they're working their way up the mountain. So there's 2 ways that we can measure the change in this person's position: where they are compared to where they were along the path. That's the measure of the arc length. or we can compare their point to some other point off in the distance. All right, and so that point that's off in the distance could be any fixed point, but what we would be looking at is some angular movement based off of that location. All right, so we would be able to come up with, like I said, an angular movement, but we could also come up with a distance relative to that location. So we would have a distance here and a distance here that I can call D1 and D2 related to the movement from position, we'll call it A, to position B. All right. So one of those is kind of what we've always been doing, and the other is, what we're working towards. Right. So if I were to tell you in really clipped, monotonous tones that the word of the day is exceptional, then you would probably write that down or immediately plug that into the survey. Yeah, so the word of the day is exceptional. But if I were to tell you that that fixed point is the origin, and that this distance is related to, the top of the mountain is some y value, it adds a little bit more context to it. It's really telling us that those line segments that I drew, D1, D2, that are separated by some angle theta, those could be vectors. So we actually can measure in terms of vector displacement, but we could also measure in terms of the individual's displacement as they move along a path. Okay, so that's being able to seamlessly go from one way of looking at things to another is really what we're working towards. All right, so we got the little blurb here. Recall that there are infinitely many ways of parameterizing a curve. I always when I throw the recalls in there, that's my way of saying I may or may not have actually said that. So this is my way of kind of sneaking it in. I think I mentioned that. I hope I mentioned it. When you're parameterizing a curve, you can decide on any expression that you want to let be the parameter. Like I could let it be equal to t. Like I can, like in that last that last problem, I could have let x squared be equal to t squared, but I could have let x squared be equal to 1/2 t squared if I wanted to. It didn't matter. Everything else would fall in line based off of what I decide to make my free variable. So with that in mind, there are infinitely many ways of parameterizing a curve. When possible, it's often useful to parameterize a curve in terms of arc length, so that each 1 unit increment in the parameter traces out exactly 1 unit of arc length on the curve, right? So it's the concept of the unit vector just in terms of a path along the curve rather than a path that's originating in space that's propped up by vectors that are originating at the origin. So to do this, recall again. It's the vector value function f of t, g of t, h of t that we define the arc length function, but now we're defining it in terms of some function u. All right, so we're allowing for a function within a function. All right, so there's a chain rule element going on here, and I can illustrate that pretty quickly. All right, so if I were to say that I wanted to have some function r of u, I could look at it in the sense that r of u is really f of u, g of u, h of u, where u is a function of t. So I'll just write it. So therefore, we could actually say that R of U, that's not a U, neither is that, would be the same as saying F of U of T, close it up twice, G of U of T, H of U of T. All right. So I'm introducing this variable U to allow a function within a function where T can be any parameter, but that parameter itself can be a function. All right. So we have our relation. S of T is equal to the integral over the interval of T sub O to T of R prime of U du. All right. So the idea, I'll just read it. The idea is to evaluate the above integral to find S of T, invert the equation to obtain T of S, and then substitute T of S into the original parameterization to obtain arc length parameterization. All right. So it's strange, but it's very doable. Right. So let me just show you how it plays out. So we have R of T. What I'm going to do is I'm going to redefine T as some function of U. All right. So let T. All right, so I would be saying R of U is equal to T squared. Well, T is U, so T squared, air quotes on the T squared, instead of the T squared, it would be U squared, I plus U J, which could also be thought of as component form, U squared plus U. All right. Now I want the derivative and then therefore the magnitude of that. So 2U plus 1. I put a plus for some reason. I got caught in the middle there. Between the IGA notation and the component form. Happens all the time. All right, so take the derivative in terms of U, all right, because I'm letting T equal U, but you could also, I mean, if you want to be really specific, T is equal to U, you could even say T is equal to U of T, you know, where U is a function of T, but you just want to have it in your mind that you're replacing T because T is a linear model, which is just like a slope and y-intercept of 1 and 0 specifically, right? So it's a line, right? Where U could be anything as long as it has a T in it, right? So it could even be the cosine of T. It could be T squared. It could be the natural log of T, right? So we're opening up the door for the vector value function to have this form, but not necessarily be this particular model. All right. So magnitude R prime of U would be equal to 4U squared plus 1 under the radical. All right. So that's what we're going to integrate. So S of T is going to be equal to the antiderivative over the interval of T sub 0 to T of 4U squared plus 1 du. All right. So that's going to be equal to S, or S of T if you want. All right. So that's the model that we're working off. Now, that lower bound, sorry, what's on my screen? That lower bound, that t sub o, that could be any numerical value, right? It's just the starting point along the graph, right? Yeah, so you can make it 0 if you want. You can make it a 20. It doesn't make a difference. It's the upper bound that makes a difference. That's the one that matters the most. All right, let me just clean this up. So this one matters the most. All right. So what we would be looking to do is anti-differentiate this. But if we're looking for a relationship, you know, it's not necessary, but it doesn't hurt to have a quick look at the picture. It breaks my heart to have to get rid of this. It took so long to type it in. And actually, it gives me an opportunity to show you. Oh man, my mouse isn't working. Why is my mouse not working? It gives me an opportunity to show you the effect of variable parameters. So let's do the curve thing again. This thing. All right, so t squared variable 0. I'll make the upper bound like 10. Oh. All right. So at first glance, it doesn't look like there's really anything going on there, but there really is. There is a parabola that exists. Now, I can manipulate my lower bound and my upper bounds to be whatever I want. So I can make it a negative 10 to 10, whatever, it doesn't make a difference. All right. So I have this information here. And what it's telling me is that I can come up with a variable expression that represents the length from any 2 points along this curve, but based off of some unknown parameter. All right. So that's the important thing to keep in mind, is that it's based off of the idea that the inner functions, whatever you're calling u, can be anything as long as it follows that model, which is kind of a really cool relationship, except you know, it's kind of a little tricky to wrap your brain around sometimes. But let's say, for example, I just want to make sure I choose something that's actually going to work. You know, let me restrict my domain so that it starts off at a 1, because I'm going to throw in a log here. Oh, I hit enter. What the hell? So I'm going to put the 1 there. I'll enter this. And let's see if I can duplicate it without screwing it up. Duplicate input. And then, come on, you son of a gun. So I just want to have the same model. So I'm going to type in ln of t. I'm going to close it up. And then I'm going to change this one also to an ln of t. And and then I'll hit enter. Okay. So now I'm going to turn off, we'll turn them both off. All right, it's still in 2 dimensions because we don't have a y component. I'm sorry, a z component, but there's enough there, I think, for you to see what's going on, and that's kind of the point, because what I did was I took the same structure, you know, u squared, if you will, you know, so something squared, and then I took that and I multiplied, or I replaced it. You know, instead of a t, I replaced it with a natural log, right? So each instance of a t got replaced with a natural log, which is great news, right? So that's really all there is to it, because what that's telling me is that even though, I mean, I didn't really look at it too carefully. I suppose we could zoom in, but you know how Geogebra really is. It's kind of a nightmare when it comes to that. But at first glance, it does look like one of them just seems to be like a truncated version of the other, right? So, and I regret even trying to zoom, because now I'm dealing with this nonsense. All right, a little bit better. So here's one of them. Here's the other. Oh, this one I wanted to go from 0. All right, better. All right, so, oh, dang it. Oh, no, it worked. All right, so we have the truncated version gone. They're both the same curve. All right, so one of them has a t squared, a t, and the other one has an ln squared and an ln. So it's basically amounting to the same thing. So it's like, wow, okay, this is working out really nicely. So what would happen if I replace the ln with, let's say, a sine? The only thing that you might run into is domain considerations. Right? It wouldn't let me do it. I mean, maybe it was going to, but I think I might have tapped away. I know this is kind of choppy. I apologize, but the GeoGebra part of it is it's always holding me up. But you know, that's kind of the idea, is that, like, if we can get these relationships down, things get a lot easier. But hopefully, I mean, if you didn't believe me before, hopefully you believe me now. You have the t squared, and the t is the general model. Now I'm replacing the t squared with a sine of t squared, and I'm replacing the t with a sine of t, so it has the same form, and so it's giving the same curve traced out, right? So that's the wonderful aspect of it. Now, if you get into the third, you incorporate a third dimension, things start getting a little crazier, but it's still the same general idea, all right? So, you know, like I said, there's a lot going on here, but the idea is that we can make an assumption that u is some function of t, and that function could be anything. All right, so it took a while to get there, but it's there. All right, and so what we would do here, again, is allow for that lower bound to be whatever we want it to be at some origin point. Now, depending on where you start, you know, you might have a different looking expression, but it'll all amount to the same thing, because it's all a relative relationship, right? So it's really how t sub o relates to t that will define the whole thing. So let's say I let t sub o equal 0. So t sub o equals 0, then if t is equal to 2, for example, that's a difference of 2. if I decide that T sub O is going to be equal to -1, and I want the difference to be equal to 2, then the upper bound would have to be equal to a 1. So the upper bound, the T, would kind of negotiate its position based off of where we start with our constant value. So if you have the ability to decide, then you would decide any way you want. Why wouldn't you pick the most reasonable value? So S would be equal to, we would say 0 to T, and then we have this integral that we have to take care of, which has a trig substitution look to it, an inverse trig relationship. It looks an awful lot like an arc tangent, just kind of on a reciprocal level. The issue when it comes to these kind of problems, well, one of the many issues, is that, like, if you can put it into a calculator, I don't know how to do it. You know, I mean, aside from the ones that, like, you know, like photo math and crap like that do the work for you, like, Desmos isn't going to help you with this. You got to be able to integrate it on your own. So what you would have to do is use your knowledge from Calc 2 to be able to integrate this. So I'm going to draw a triangle, right, with the value theta. I'm going to use a trigonometric substitution, because it's not just a simple matter of being able to say, well, you know what, why don't I do U substitution or something like that. I mean, maybe you could do something with integration by parts, but I find that the trig substitution ends up being the nicest way to do it. All right. So if I'm going to be able to handle this the right way, we would know that one of the legs would have to be a 2U, another would have to be a 1, in order for the hypotenuse to end up being the root of the squared values added together. All right, that's one possible arrangement. Another possible arrangement would be maybe the ones and the 1 and the 2U could be swapped. All right, but at least in this way, it allows me to use a tangent. Tangent of theta is equal to 2U over 1, opposite over adjacent, to make that substitution, because then tangent squared theta would be equal to 4U squared. Now I have a direct substitution. All right. So this can now be replaced with that. The problem is I have a du that I haven't accounted for yet, so I gotta sort of create that. Right. So we could do this substitution if we want. Another substitution that you could actually do would be relating, you know, it's all right triangle trig. You could say secant of theta is equal to the entire square root or U squared plus 1 over 1. The idea being that secant is adjacent over hypotenuse. I'm sorry, hypotenuse over adjacent. Geez Louise, it really is the end of the week. All right, and so we can do a direct substitution that way also. But we still need to be able to swap out the du. So if we can do that, then we'll be kind of off to the races here. So I'm going to need to take a derivative here. I think this is the best candidate. Tangent theta is equal to 2u. So secant squared theta, well, you know what? Let me solve it for you first. Make it as easy as possible. U would be equal to 1/2 tangent theta, which would make du equal to 1/2 secant squared theta d theta. And so now, instead of actually swapping out just the tangent and having to do some more trigonometric substitutions, what I can do instead would be to swap out the entire radical. Oh, that looks terrible now. Make that look a little nicer. Swap out the entire radical for a secant theta, and then swap out the du for this, clean it up and go from there. All right. But we also have the bounds. So it's like, oh man, this thing is spiraling out of control. Actually, it's going to get a little bit nicer in a second. You could leave it boundless until you reverse substitute it, integrated it, and reverse substitute it. I think that's probably the best way to go, rather than finding u of 0 and u of t. I think that's going to make things overly complicated. So what we'll do is we'll say, as an extension here, that s is equal to just the indefinite integral of secant theta. And then that's going to be multiplied by 1/2 secant squared theta d theta, because that's what's swapping out the du. All right. So then we can clean it up from there. You know, we can consolidate. But then we have to integrate this guy. All right. So that's where some other substitutions come into play. But you know, you kind of, I don't know if you learned this from experience or what, but you might have discovered over time that maybe not doing it that way, you know, like leaving it separate is probably the better way to go, just because you're going to have to make a substitution anyway. So why not, you know? So I'm just going to kind of remind you of some basic rules just back from pre-calc. It was in the end of the Unit P packet. Never hurts to look this over. Remember, sine squared theta plus cosine squared theta is equal to 1. And these rules are going to come up over and over again, so it's never a bad idea to rehash them. If I divide each part of this by sine squared theta, I would end up with 1 plus cotangent squared theta is equal to cosecant squared theta. And then if I divide each part of this by cosine squared theta, I get tangent squared theta plus 1 is equal to secant squared theta. All right, so something like that could be a helpful substitution, because that would allow me to swap out the secant squared for a 1 plus tangent squared. All right, so you know, it's like in those moments where you're like, well, which one's going to be the better way to go? It all depends on, you know, your knowledge base. I mean, if you happen to know the antiderivative of secant cubed, then by all means go for it, right? But if you have to invent it, then the substitution might be the way to go. But you know, one way or the other, we need it. So that's what we're going to do, is we're going to replace the secant squared with a 1 plus tangent squared. So then we'll distribute. You can actually pull the 1/2 out of the whole thing if you want. I'm just going to leave it in for now. Except if I leave it in, I really got to leave it in, right? All right, so this whole thing is equivalent to the 1/2 secant cubed theta. So we just want to kind of keep that in mind. But we're at a point where we can evaluate, at least figure out one part of it. That's this piece. The other part, you know, we got a little work ahead of us, but you know, it's still doable. All right, so we got that one piece anyway. have this moment of regret where I probably shouldn't have led with this problem. The next one's so much easier. Actually, probably rather show you that one in a second because I know we're going to run out of time, but we can at least get a few more steps in here. So again, we know that this is going to be equal eventually to the 1/2 secant cube theta. But then you look at this and you say, okay, well, this, what this are you speaking of, sir? This. So you look at that and say, well, what are my options for integrating that? Another substitution. Well, that's just going to possibly bring it right back in a circle. You could also look at it by integrating by parts. So you can try using the parts technique. Right, so right, so when you're dealing with integration by parts, it can get a little messy, but it's still very doable. Right? Let me just resize a little bit. Today's class is the class of like, yeah, it did not give enough room for anything. Right, so you can look at this and say, you know, it's a uv minus the integral of v du. So you define a u, define a dv, and you look at the u and the dv as expressions that should be easy to differentiate or anti-differentiate, depending on need, of course. But this I would look at as 1/2 secant theta tangent theta times tangent theta. If you look at it and say, well, what's the antiderivative tangent squared theta? Honestly, that's kind of one of those things where it's like, if we knew that, we wouldn't be really going down this road, right? Secant theta tangent theta is something very easy to anti-differentiate. So we put that here. And then maybe the 1/2 can go along with the u, so tan theta over here. So differentiate, the u would be equal to 1/2 secant squared theta d theta. You really got to thin out the marker here. Shrink it down, thin it out. For some of us, this brings back like great memories from Calc 2, and for some others, it's like, why are you doing this? So v, the antiderivative secant, tangent and secant, so secant theta, so uv minus the integral of v du. So 1/2 tan theta secant theta. Well, I'll write the secant first just because it feels better. Minus the integral of the v multiplied by du. So you'd look at it and say 1/2 secant cubed theta d theta, and you'd think, oh my God, there's no way. You got to be kidding me, dude. Now you were going back in a big old circle, and this is the thing that it's a great moment or a terrible moment, depending on your feeling about math. We got to remember that our ultimate goal here was to figure out the value of 1/2 secant secant cube theta. That was the ultimate, that was the objective, right? So this whole journey started off because we were looking for this guy. So the left-hand side of the equation is in fact a 1/2 secant cubed theta d theta. You pop in a little equal sign there. The right-hand side is this big old mess, admittedly, but part of which is another 1/2 secant cubed theta d theta, which I can now add to the other side of the equation. So it's combining like terms. It's just not pretty, or it's beautiful, like I said, depending on how you feel about things. But eventually you get there. It's just, you know, what goes up must come down. Now we got to start the journey of reversing the whole process to get us to the antiderivative that we were looking for to begin with, right? But this is all going to amount to, you know, half plus a half as a whole. The antiderivative of secant cubed theta d theta is going to be equal to, so this cancels, this expression plus this expression. And unless I miss something along the way, that stuff is then going to be added. Well, actually not even added, because that's what we're looking for. We just got to pop 1/2 in front of that, and then we'll be in good shape. Right? So we're looking at long last, I'll just jot it somewhere. I don't even know. Equal to this one plus this one. All right. So then it kind of begs the question, because again, the arc length S, we had redefined the variables so that it would be in terms of theta. Now we have a choice in the matter, and that is to bring everything back to be in terms of t, or we can convert t over to make it look a little nicer. I don't know. There's no guarantee it will look nicer. All right. So let me again resize and move some things over. All right. So this expression here can now be thought of as S equals, well, we got the antiderivative of secant cubed is equal to all that stuff. We want half of that. So I would chop I would chop everything in half. So 1/4 the natural log of secant theta plus tangent theta plus 1/4 of secant theta tangent theta. So I'm going to just write plus secant theta tangent theta, and then just put parentheses in front of the, you know, separating the 1/4. All right. So like I said, it's not pretty, but it's something. All right. Now S is really, again, the arc length, but we want to have this in terms of t. So I can now reverse substitute, because I know that secant of theta is equal to the square root of 4u squared plus 1. Tangent theta is 2u. So I can make those substitutions. All right. So another resize coming up. So S would be equal to 1/4 times the natural log of the secant, which we defined over here as being the square root of 4u squared plus 1, plus tangent, which we defined over here as being 2u, And so we can make those substitutions again. Square root of 4u squared plus 1 times 2u. So I actually can just kind of tuck that in front. All right. So that's what S would be in terms of u now. All right. So we reverse substituted. So now I can plug in the t and the u respectively. So now I can integrate. I have my integral, and I can make my substitution of the interval of 0 to t, and get S equals 1/4. Everything is now going to be replaced to have t's instead of u's. I just want to have a quick look and make sure that substituting in a 0 is actually going to zero things out, right? So, because we have a natural log in there, so I'm just actually going to write the next step as 1/4 ln. So ln of 4 times 0 plus 1 is going to be the natural log of 1 plus 0, which is a 1. Natural log of 1 is equal to 0. Everything else zeroes out. So this actually would be a meaningful part of the expression. So I'd want to keep that in there. But it is going to cancel out anyway, because the natural log of 1 is equal to 0. So, you know, it's up to you how you define something to be meaningful. It's just there was still a function there, and it was a function of a value. So I figured I'd throw it in at least to show the step. All right. So now I have a relationship between S and T. Now this is where the process is either going to work out or it's going to fall apart. You can see here, this is a big old mess, but our goal is to find an arc length parameterization, which would require us to swap out the t in our original vector value function for what t is equivalent to in terms of r. I'm sorry, in terms of s. All right. So what you would have to do at this point, and we're out of time, but also even if we weren't out of time, I mean, this is kind of a bear. I just realized this should be a t now. I made it a u for some reason. You'd have to solve this for t in terms of s. So then solve for t in terms of s. Then rewrite r of t, replacing all t's with the above expression. All right. So whatever expression you come up with, that's what you would swap in for the t, and that would make your what we call the arc length parameterization. So it would be a new function that would be strictly in terms of the arc length, rather than being in terms of whatever the parameter t was. All right. So I know that was a lot. That it was a terrible idea to lead with that example, but the benefit on your end, if you've survived that example, is that you get to try this example on your own. And this example is like a bazillion times easier, right? So this one you'd be done within like 5 minutes. This one took like an hour. Number 4 took like an hour. Number 5 it'll take you like 5 minutes. But that's where we'll pick up next time, right? So I apologize for that. It's a little beefier of a problem than I intended, at least to start off the concept, but it really, it was a function of the integration component. If the integration part of it was easier, it would have been fine, but it just wasn't. All right. So so that's where we're going to leave it. Like I said, if you have any questions, stick around. Otherwise, enjoy the rest of your evening, and I will see you all on Tuesday.
Thank you.
You're
Thank you,
welcome.
Professor.
Thank you, Professor.
You're welcome. Take it easy.